This video shows how to audit the behavior of an autonomous system whose policy is captured in a Kiel cognitive engine. In this case, we are using a hypothetical policy that is demonstrated in a simulation on CompSim's website. It is demo number 1, titled UAV Demo, should you want to watch the policy in action. The policy was created using the Kiel dynamic graphical language. The source code for this policy is rendered in demonstration number 2. The purpose of this video is to show how easy it is to audit the behavior of an autonomous system if the policy controlling the autonomous system is created using the Kiel dynamic graphical language. Now a couple of things to consider about policies, the execution of policies, and the auditing of behavior. First, policies guide the behavior of a system. They are almost always continuously being reevaluated because the environment is constantly changing. For example, as an autonomous system moves around during its mission, it is constantly using fuel. The availability of fuel, at least in this example, is a contributing factor that influences how the UAV considers its options. If the UAV is just flying around looking for a target, it is probably not appropriate to audit that behavior every millisecond. On the other hand, if the UAV suddenly decides to go home in the middle of a mission, it may be appropriate to review why that decision was made. When you consider auditing the behavior of an autonomous system, you will probably be reviewing data that was recorded in the autonomous system's flight recorder. This data can be used to animate the Kiel dynamic graphical language. This makes it possible to trace any decision or action of the autonomous system to the root cause in a very short amount of time. The policy that drives the 2 UAVs in demo number 1 has 3 segments. It is choosing between mutually exclusive options. In this case, the UAV can be performing only one of the planned actions. It can search for a worthy target. It can attack a target if certain conditions are met. It can make an evasive maneuver if it is threatened. It can hide if that might be a better choice than to attempt to evade the threat. Or it can retreat or decide to go home. The policy is also dictating how to avoid collisions with another obstacle. That would interrupt the planned decision-making. It also defines when to shoot, which would be a secondary decision once the UAV has decided to attack the target. In this video, I will walk through the process of reviewing the scout, attack, evade, hide, retreat decision, as this type of decision is one that is most likely to demand an audit. Before getting into the auditing process, I want to give you a very brief overview of the Kiel language. This is not a tutorial on the language, but you don't need to know everything about the language to be able to audit the behavior of a system. So first, this is the Kiel source code. Outputs are shown as vertical bars at the top of the window. Outputs can represent the decisions or control actions made by the system, or they can be information fusion points where information is collected and combined and then used to influence other pieces of information. Outputs are called positions in the Kiel language. Inputs are shown as vertical scroll bars across the bottom of the screen. You will notice that they are grouped below the positions that they drive. Inputs are either supporting or driving inputs, or they are objecting or blocking inputs. The supporting inputs are tagged with a green triangle pointing up, and the objecting inputs are tagged with red triangles pointing down. So if you see a position with 1 green input and 2 red inputs, you have a position that has 1 reason to do something and 2 reasons not to do it. Inputs are relative, somewhere between no and yes, or no impact or maximum impact. They are shown as vertical scroll bars, so they can indicate value or significance of an input. The position bars, the ones at the top, show 2 pieces of information. The height of the bar is an indication of importance. The blue area within the bar shows the integration of the driving and blocking inputs. The Kiel dynamic graphical language includes a number of wires. The wires define functional relationships between information items. To audit the behavior of a system, you trace the wires from the decision back to the source. In this example, we are choosing between mutually exclusive options. The options are attack, retreat, evade, hide, and scout. And with the snapshot of real-time data, as we are showing at this instant, the decision is made to scout, or search for a worthy target to engage with. With the mouse, I click on the input that drove the final scout decision. The red wire leads me to the position that drove that decision. This is the scout accumulator position that is driven by 4 inputs. The input with the black arrow pointing up is called a bias. It is a supporting input that is locked at 100. Essentially, the policy says to scout if there are no reasons to do anything else. And in this case, we have sufficient weapons to continue on. There are no threats to be concerned with, and we haven't found a worthy target yet. So it took about 5 seconds to trace the scout reasoning and 30 seconds to explain it in this video. In this next audit, we see that the decision was made to retreat. We can look at the accumulators for all the options and see how they compared. To see why, we click on the input that drove the retreat decision. In this case, we can see that it is the best option, but only slightly better than making an evasive maneuver decision. We can see the retreat decision is driven by 3 factors: weapons concern, damage assessment, and fuel. Of these 3, damage assessment carries the most weight with a 48.8 impact, followed by weapons concern that carries a 10 impact, and that was followed by fuel concern with a 4 impact. In our example policy, retreat is the least desirable decision. It is only acceptable if the mission has been satisfactorily completed, which was to find and engage a worthy target. In this case, we can see our UAV found a reasonably acceptable target that was identified to have a value of 60. So why didn't the UAV decide to attack? I click on the input driving the attack decision. This takes me to the attack T position and see that it is driven by 2 inputs. It has no value here. It is also not blocked. I click on the 0 input and trace it to the threshold, where I see that there's only a small reason to attack. To determine how our target value was reduced from 60 to a much lower value of 12.1, I trace the signal to its source. Now I see the original perceived target value of 60, but I can quickly see how the value was reduced. I see the UAV determined that there was some risk in attacking the target, a value of 30. It shows that there was added risk due to diminished weaponry, weighted at 10. It shows there was more risk associated with a self-damage assessment, weighted at 20, and a significant risk due to another threat that was detected, weighted 60. So even with a target rated at 60 out of 100, the result of the risk assessment drove the accumulated value down to 12.1, which is less than the threshold that a target must be valued at in order to proceed with an attack. Now I am going to show another audit. This time the decision is made to attack a target. This is potentially the most important audit to ensure that the attack is made according to official rules of engagement and international law. It is important to note that this is just a hypothetical policy of a simple demonstration, not a fully functional authorized policy. It is just provided for training purposes. So first, we can see that the UAV has decided to attack the target. We can see that the UAV detected the same target value of 60 as in our previous example. We want to know why the decision this time was made to attack. By clicking on the input driving the attack decision, we can trace it to its source, the attack T accumulator, that is driven by 2 inputs. A blocking input that is not active has a value of 0, and an input that is rated at 100. This is the key driver, so I click on this input and trace it to its source. As in our previous example, the source is a threshold. In this case, the resolution of inputs has driven the value over the threshold, thus turning it on. We can see that the attack was not blocked because there was no weapons. And this time we can see that the accumulated target value is 24.54. and that this is above the threshold value of 20. Now tracing to the source of the 24.54 value, we see that our target value here is rated at 72 rather than our initial perceived value of 60. Let's trace backwards and see why. First, we see our locally sensed target value of 60, but we see there is another factor driving the target value higher. The target value modifier is set at 30. Tracing this value to its source, we can see that it comes from the WMD modifier. The input to this is the risk modifier input that, in our Demo 1, comes from the mission control adjustment. In this demonstration policy, the mission control adjustment signifies an external message that can be supplied by a ground commander to influence the behavior of the UAV. This gives the ground commander some limited authority to influence the behavior of the UAV without exerting direct remote control. The ground commander is influencing how the UAV thinks, and in this case, making the UAV think that the target is somewhat more important than it thought it was based on its own internal sensors. Now returning to our accumulation of reasons to attack and reasons not to attack. Now we know why the perceived target value was increased from 60 to 72. We can see that our target risk is 21. Tracing this to its source, we can see that the observed risk was 30, but this is reduced by a 30% blocking signal. Tracking the 30% reduction in target risk to its source, we can again see that this comes from the WMD modifier, which is driven by our mission control adjustment. So we can see that the mission control adjustment makes the UAV perceive that the target is more valuable and that the UAV itself is more risk tolerant, which is how the policy allows for ground control to change how the UAV thinks. Now back at our accumulation of reasons to attack again, and looking at the risk associated with diminished weaponry. We can trace this signal to its source, the weapons available, and locally measured value. We can also see that the magnitude can be traced back to the WMD modifier. So again, the mission control adjustment has made the UAV more risk tolerant by reducing the impact of diminished weaponry. The next risk factor in determining the accumulated target value is damage impact. Tracing this to its source, we can see that it is the locally measured value. There is no risk modification to damage assessment. Finally, there is the threat assessment. We can click on the input and trace it to its source. We can see the observed threat value of 60, and another factor that reduces its impact. If we trace this value to its source, we see again it is influenced by WMD modifier. So now we know that the mission control adjustment has impacted the target value by making the UAV perceive that the target value is higher than its own local observation said it was. And it has impacted 3 of the 4 risk factors by reducing their impact. Perhaps we want to look at the model to see visually how our policy allows for ground control to impact the decision. Since we are just reviewing the policy in an after-mission review, we are dealing with just copies of real-world data. We can use the dynamic nature of the language to visualize the entire impact. To do this, I will manually manipulate the risk modifier input and watch the dynamics. To audit the behavior of an autonomous system, one is looking at the values observed by the system, along with externally supplied inputs, all of which are combined to make decisions and take actions. The graphical nature of the Kiel dynamic graphical language makes it easy to see these values and see how they are combined to make the decisions and exert relative control. This video focused on the auditing process and not the policy creation side. One additional service provided by the Kiel Toolkit that can provide assistance in looking at just a portion of the policy is to choose a decision or output and look at and find all the factors that contribute to that decision or action. For example, looking just at the decision to attack, we can see all the factors that contribute directly to the decision and hide all others. Similarly, I can look at our WMD modifier and see all the ways this signal impacts the decision-making process by influencing how the UAV thinks. In summary, the Kiel dynamic graphical language makes it easy to see the influence of valued information and see the functional relationships within the policies driving autonomous systems. The development of Keil-based policies, as well as the auditing of those policies, can be accomplished by subject matter experts without higher-level mathematics or software engineering prerequisites. Tracing the wires makes it easy to visualize the influence one factor has on others. Named views, as well as parent and child views, provide additional ways to visualize dependencies and the information fusion process. As subjective decisions are migrated to machines, those decisions must be mathematically explicit, because that is just how machines interpret information. Displaying the logic behind the policies graphically makes it easy for humans to validate those decisions and actions controlled by the policies. Allowing humans to interact with the logic provides an additional aid to the auditors as they confirm the systems are working the way they want them to work. While this was not a tutorial on the Keil language, hopefully you can understand how easy it is to trace decisions and actions to their underlying reasons, even without a formal class on the language. I have shown how the Keil dynamic graphical language provides a way to perform a detailed analysis of the decisions and actions executed by an autonomous system. You can see the exact values of the information items that were used at the point in time when the information was recorded. You can see exactly the root cause of a decision or action by tracing through the information fusion process. There are, however, other times when a higher level review of the policy might be desired. In this case, the reviewer may be primarily interested in what information was used to drive a decision or action, and by a process of elimination, the reviewer can see what was not considered. An influence diagram provides this information. Here I am showing the same Keil policy for our UAV in the left window, and I have opened the Keil Influence application in another. The Keil Influence application uses the actual policy from the Keil toolkit to generate the graphics for the influence diagram. Once the balls are dropped on the screen, they can be dragged around for clarity. The large green balls are inputs to the policy. The large red balls represent outputs of the policy. The gray balls indicate information collection points or information fusion points. Each ball has a label that came from the Keil dynamic graphical language used to create the policy. You can turn on or off individual labels by clicking on the balls. There is a menu item that allows you to turn on or off all the labels at one time. One of the primary reasons for creating an influence diagram is so it can be used as a chart in a document or presentation. A menu item allows you to copy the influence diagram to the clipboard so it can be pasted into another document. Here I am showing the influence diagram pasted into a Microsoft Word document. Another feature is the ability to highlight just a portion of the influence diagram. Here I am highlighting just the shoot logic. Like before, I can copy and paste this section into the Word document. In this example, I have shown how to create a dynamic influence diagram using the Keil Influence tool, and how that tool enables the creation of static influence diagram images that can be pasted into other documents. We have one other tool that compiles the influence diagram into an Adobe Shockwave file. This allows you to create interactive influence diagrams that can be inserted into PDF documents. In summary, policies created using the Kiel dynamic graphical language can be executed by autonomous systems. At key points in time when certain decisions need to be audited to validate the behavior of the autonomous system, these decisions and actions can be revisited by loading the inputs into the Kiel toolkit. It is easy to trace how those valued inputs influence the decisions or actions with very little training on the language itself. The same policy can be used to create high-level influence diagrams that can be used to review the policy without requiring any understanding of the Kiel language.